In the world of artificial intelligence, we're witnessing a monumental shift. We've moved beyond simple chatbots that answer questions to a new paradigm, AI agents. These are not just responders, they are doers. Autonomous systems that can reason, plan, and execute complex tasks on our behalf. In this video, we'll dive deep into the architecture of modern AI agents, exploring everything from their core components and memory systems to the frameworks used to build them, the critical importance of responsible AI, and how to deploy them into the real world. So, what exactly is an AI agent? At its heart, an agent is a system designed to perceive its environment, make decisions, and take actions to achieve a specific goal. Think of it like a digital employee you can delegate tasks to. The core of any modern agent is a powerful large language model, or LLM, which acts as the brain. This brain is then augmented with three critical components. First, a set of tools which act as its hands to interact with the world. Second, a memory system to learn and recall information. And third, a planning module to break down complex goals into actionable steps. Agents operate on a continuous cycle, often referred to as an agentic loop. A popular and effective framework for this is REACT, which stands for Reason and Act. It works like this. First, the agent observes its current state and the user's request. Second, it thinks or reasons about what to do next, forming a plan or identifying a specific tool to use. This reasoning step is crucial. It's where the LLM's power shines. Finally, it takes an action, such as calling an API or asking a clarifying question. The result of this action updates the environment, and the loop begins again, continuing until the final goal is achieved. The large language model is the central nervous system of the agent. It's the reasoning engine that powers the think step in our loop. Models like OpenAI's GPT-4, Anthropic's Claude 3, or Meta's Llama 3 are not just text generators, they are powerful few-shot reasoners. When presented with a goal and a set of available tools, the LLM analyzes the problem, breaks it down, and decides the most logical next step. Its output isn't just a sentence, it's a structured decision, often in a format like JSON, specifying exactly which action to take and with what parameters. The quality of this reasoning directly determines the agent's capability. To effectively guide the LLM's reasoning, we use a specialized form of prompt engineering. Instead of a simple user query, we provide the model with a detailed system prompt or metaprompt. This prompt acts as the agent's constitution. It defines its persona, its primary goal, the constraints it must operate under, and, most importantly, a detailed description of the tools it has available and how to use them. A well-crafted system prompt is the difference between an agent that is unfocused and one that is reliable, predictable, and effective at its designated task. It sets the rules of the game for the AI. For an agent to be useful, it can't have amnesia. It needs memory. We can categorize agent memory into two types. First is short-term memory, which is essentially the LLM's context window. This includes the recent conversation history and observations. It's fast but finite and gets cleared after the interaction. Second, and more powerfully, is long-term memory. This is a mechanism for the agent to persist and recall information across many interactions. It's like the agent's personal knowledge base, allowing it to learn from past experiences or access vast amounts of external data that won't fit into the context window. So how does long-term memory work in practice? The most common approach is using a vector database. Here's the process. First, you take your external documents like PDFs, past conversations, or a knowledge base and break them into smaller chunks. Each chunk is then passed through an embedding model, which converts the text into a high-dimensional numerical vector. These vectors are stored in a vector database. When the agent needs information, it embeds its current query into a vector and performs a similarity search in the database. The database returns the most semantically similar chunks of text, which are then fed into the agent's short-term memory to provide relevant context for its next action. If the LLM is the brain, tools are the agent's hands and senses. Without them, an agent is just a conversationalist trapped inside its own model weights. Tools allow an agent to interact with the outside world. A tool can be anything from a simple calculator or a Python code interpreter to a complex API call that searches the web, queries a database, sends an email, or books a flight. By providing an agent with a well-defined set of tools, you grant it specific capabilities, enabling it to go beyond its inherent knowledge and perform real, tangible actions in the digital or even physical world. Let's walk through a concrete example. A user asks, "What was the weather like in New York yesterday?" The agent's LLM brain, guided by its system prompt, recognizes that it cannot answer this from its internal knowledge. It sees a Get Historical Weather tool in its list of available tools. The LLM then reasons that it needs to call this tool and constructs the necessary arguments, sit in New York and date yesterday. This structured output is passed to a tool executor which actually runs the code. The tool returns the weather data, say 15 degrees C and rainy. This new information is added to the agent's context, and in the next loop, the LLM uses it to formulate the final answer for the user. Building all of this componentry from scratch can be complex. This is where frameworks like LangChain come in. LangChain is an open-source framework designed to simplify the development of applications powered by LLMs, especially agents. It provides a modular set of abstractions for the core components we've discussed. It has integrations for hundreds of different LLMs, tools, and vector stores. It offers standard, interoperable interfaces for prompts, memory systems, and parsers, allowing developers to easily compose these building blocks into powerful chains and autonomous agents, abstracting away much of the boilerplate code. Let's see what building an agent with LangChain looks like at a high level. First, you define your tools. LangChain makes this easy with a simple decorator. You can write a standard Python function and just add tool above it. Next, you select your LLM and bind your tools to it, which tells the model what functions it's allowed to call. Then, you create a prompt template that instructs the agent on how to behave and formats the inputs. Finally, you assemble these pieces into an agent executor. This object takes the user input, orchestrates the React loop we discussed earlier calling the LLM, and tools in turn and returns the final result. It manages the entire agentic loop for you. Another powerful way to build agents, especially if you're already in the OpenAI ecosystem, is the Assistant API. Unlike LangChain, which is a library, the Assistant API is a managed, stateful service. It handles much of the complexity of agent development for you, particularly state management. The core concepts are the assistant, which is the configured agent with its instructions and tools, the thread, which represents a single conversation and maintains its state over time, messages that are added to the thread, and a run, which is the process of the assistant executing on the thread's messages. It automatically handles the conversation history, so you don't need to manage it yourself. The workflow for the Assistant API is fundamentally asynchronous and based on API calls. First, you create an assistant object once, defining its model, instructions, and enabling built-in tools like code interpreter or knowledge retrieval. When a user starts a conversation, you create a thread. You add the user's message to this thread. Then, you create a run, telling the assistant to process the messages in the thread. You then have to poll the status of the run. The run status will move from queued to in progress, and eventually to completed or requires action if it needs to execute a custom tool. Once complete, you can retrieve the new messages added by the assistant from the thread and display them to the user. So, when should you use LangChain versus the OpenAI Assistant API? LangChain is an open-source framework, giving you maximum flexibility and control. It's model agnostic, so you can swap out GPT-4 for Claude or an open-source model. You have fine-grained control over every part of the agent loop and memory. The Assistant API, on the other hand, is a managed service. It's less flexible but significantly simpler for use cases that fit its structure. It excels at managing conversation history and state, offloading that complexity from your application. The choice often comes down to control and flexibility versus speed of development and managed infrastructure. As we build more autonomous agents, ensuring they act safely and responsibly is paramount. This is not an afterthought. it's a core design requirement. Agents introduce unique risks. They can hallucinate and take actions based on false information. They can be manipulated through prompt injection, where a malicious user tricks the agent into performing unintended actions. They can handle sensitive data, creating privacy risks. And most critically, if connected to real-world systems, they could take harmful or irreversible actions. We must build robust safety layers to mitigate these dangers before deploying any agent. How do we build safer agents? We use a multi-layered approach. First, we implement guardrails. These can be input/output filters that check for harmful content, or specific logic that constrains the agent's behavior. For example, a guardrail could prevent the agent from ever calling a delete database tool. Second, we use validation. Before executing a potentially destructive action, the agent can be required to get confirmation from a human. This human-in-the-loop approach is critical for high-stakes tasks. Finally, we must rigorously test our agents against adversarial attacks, trying to break their safety protocols before they are deployed. Once your agent is built and tested, you need to deploy it. A common pattern is to wrap the agent logic in a web server, like one built with Fast API or Flask, and expose it via an API endpoint. This can then be deployed using various strategies. For simple, event-driven agents, serverless functions like AWS Lambda or Google Cloud Functions are a great, cost-effective choice. For more complex, long-running agents, containerizing your application with Docker and orchestrating it with Kubernetes provides scalability and resilience. Regardless of the method, robust logging and monitoring are crucial to observe your agent's behavior in the wild and catch any issues quickly. A fundamental limitation of today's LLMs is their fixed context window. While these windows are getting larger, they are still finite. For an agent working on a very large codebase or a long, complex task, this becomes a major bottleneck. The agent can only see a small portion of the relevant information at any one time. The current solution is retrieval augmented generation, which we discussed with memory, but this is a reactive process. The application decides what to stuff into the context. What if the model itself could realize it's missing information and proactively ask for it? This leads to an emerging idea called the Model Context Protocol, or MCP. It proposes a new, standardized way for models and applications to communicate about context. Instead of the application always pushing context to the model, MCP would allow the model to pull context on demand. Imagine an agent is analyzing a huge repository of code. It might realize it needs to see the definition of a function in another file. With MCP, instead of hallucinating, it could emit a special getContext call, asking the hosting application to provide that specific piece of information. This would allow models to dynamically explore vast amounts of context, far beyond their fixed window size. We've covered a tremendous amount of ground, from the foundational components of AI agents, LLM Brain, Memory, and Toolsto, the powerful frameworks like LangChain and the OpenAI Assistant API that help us build them. We've stressed the non-negotiable importance of building in safety and responsibility from day one, and we've looked at the future with concepts like the Model Context Protocol. The era of autonomous agents is just beginning. As developers, you are the architects of this future. The tools are here. Now it's time to build.